Good morning, everyone. It's an honor to present our recent research at IEEE SMC 2025. Today, I will introduce our work on enhancing non-dominant sorting genetic algorithm 3 using chaotic dynamic and estimated convergence point. This is my outline. There are 5 parts in my outline: background, motivation, numerical evaluations, research result and analysis summary. First, I will introduce my background. Multi-objective evolutionary optimization algorithm, MOEA. MOEA algorithm is a global optimization search method that simulates the evolutionary mechanism of biological organisms and began to develop rapidly in the 1990s. The MOEA is efficient and effective to handle the multi-objective optimization problem. In this uh, we, in this figure, we can know most of them has multiple objective and need to be satisfied at the same time. The red line is an ideal state of resource allocation. Allocation. Part. This is Pareto. The principle of chaotic evolution is to simulate chaotic traversal motion to achieve source. The dots in the figure are iron molecules, and the red triangle represents the global optimal. The air factor moves randomly and research the global optimal at least once. Then I will introduce chaotic evolution algorithm. We propose a novel evolutionary computation algorithm that fills the evolutionary intervention and the chaotic audacity. We call it as chaotic evolution. CE. Chaotic motion has a lot of kinetic properties such as audacity, randomicity, and so on. We can see this figure on this slide to get a better understanding. Choose one individual to be the target vector. We can generate a mutant vector by a formula. Then the chaotic vector is generated by crossing the target vector. And the mutant vector, chaotic vector is an upstream that comes from a target vector by simulating the chaotic behavior in the search space. Estimated convergence point method. We can find a set of the pairs of moving vectors in a parameter space in accord with the Pareto dominance information obtained in an objective space. We can use the moving vector information to estimate a convergence point that presents a promising error, where Pareto solution would be in a parameter space. We put such an estimated convergence point of a parameter space into EMO search and remove one of the dominant solutions. EMO search should be enhanced considering such search information, and hopeful EMO algorithm can find more non-dominant Pareto solutions quickly. That is a study motivation of our proposal that analyze his estimated convergence point to accelerate EMO search. NSGA2, non-dominated sorting genetic algorithm 2. NSGA2 is an improved version of NSGA. NSGA is one of the EMO algorithms which have the capability of finding multiple Pareto optimal solutions with a single simulation running. The SGA2 introduced the fast non-dominated sorting and animation main selection using crowding distance. Then I will introduce non-dominated sorting genetic algorithm 3. There are 2 parts in this algorithm: fast non-dominated sorting and the reference point method. About the reference point method, first define the reference line connecting the reference points and calculate calculate the vertical distance between the individuals and the reference length. Each individual is also associated with a reference point based on the minimum vertical distance, and calculate the number of individuals associated with each reference point. Finally, select K individual based on the number in the step 4. Part 2 is motivation. We add the chaotic evolution into MOE algorithms. About chaotic evolution, first is to generate a mutant vector from a target vector, and then intersect the target vector with the mutant vector, and we generated a chaotic vector. About optimal algorithm framework, in this study, we explore ways to incorporate chaos optimization theory and estimated convergence point method into the NSGA 3 to improve performance in multi-objective optimization problems. In the initialization phase of the algorithm, we deploy chaotic sequence to generate the initial population. The algorithm estimates a convergence point based on the current Pareto from to get the exploration towards less represented area. The part 3 is the numerical evaluations. First, we use state function as multi-objective benchmark problems to investigate the optimization performance. The population size of the all evaluated algorithm is set to 100, and we evaluate each algorithm with 1,000 generations. We run all the experiments with 20 running. For each running trail, each algorithm is set with the same initialized population for fair comparison. Multi-objective benchmark problem, ZDT function. About the multi-objective benchmark problem, we choose 5 ZDT functions. Every ZDT has 2 functions, ZDT1, 2, 4, and ZDT6 usually use real encoding. That is, the solution consists of continuous variables. In contrast, ZDT5 uses binary encoding, and its solution consists of a set of binary strings. This coding difference requires ZD5 to require additional transformations or special processing strategies when using traditional real number-based evolutionary algorithms. So we don't use ZD5. About evolutionary evaluation metrics happy volume. In animals, the algorithm products a set of points in the performance space as an estimation of the Pareto from. One of such methods is the happy volume indicator, which gives the happy volume between the estimated Pareto from and the reference point. The larger the value of happy volume, the better the performance of the corresponding algorithm. Next one is inverted generational distance. IGD is a comprehensive performance evaluation index. It mainly calculates the minimum distance sum between each on the real Pareto frontier and the individual set obtained by the algorithm and evaluates the convergence and distribution performance of the algorithm. The smaller the value is, the better the overall performance will be. Last one is comparison analysis. Uh, by this figure, we can gain insight into the temporal dynamics of algorithm performance, how quickly and efficiently each algorithm approached the optimal from. A detailed pair with comparison of the Pareto from points generated by the algorithm in each generation. This comparison involves plotting this point on a graph to visually assess the convergence and distribution of the solutions toward the Pareto from. We can visualize the evaluation of these fronts over successive iterations. Next part is research result analysis. First, I will introduce the mean happy volume and IGD of five benchmark functions used in the experimental evaluations. Uh, we can get something from the table 1 and table 2. The proposed ECNJ3 and ECNJ2 achieved the highest happy volume and lowest IGD value across most city test functions, indicating superior convergence and diversity. Particularly on ZD4, ECNJ3 shows outstanding performance in handling complex multimodal landscapes. Then, this figure is about a average number of Pareto frontier solutions in each generation. Mm, from these figures, we can know in the case of ZT13, ECIJ3 shows superior performance as depicted by the graph's higher and more steep lines. This indicates that the NSGA3 in integrating both estimate, uh, est- estimated convergence point and chaotic dynamic is beneficial in effectively employing and exploiting the solution space. Across all test functions, ECNJ3 and ECNJ2 consistently outperform the other four algorithms in different DDT functions, highlighting the advancement in handling multi-objective problems by the newer generation algorithm. Statistical analysis. The bar chart reveals that the ECNJ3 and ECNJ2 show competitive performance, occupying the first and second ranks respectively. The Bifferoni down test analysis explicitly that the enhancement in ECNJ3 have a statistically significant impact on its performance. The the part is a summary. First, I will first about the summary about the happy volume and AD. The happy volume result clearly shows the ECNJ3 constantly achieves the highest happy volume values across most ZT test functions. This confirms that the combination of chaotic dynamics and estimated convergence points significantly improve diversity and prevent premature convergence. About IGD, the IGD result demonstrate that ECNJ3 provides a close approximation to the true Pareto from, with notably lower IGD values in ZDT3 and ZDT4. This finding indicates that the dual enhancement strategy enables more accurate convergence and well-distributed Pareto solutions. The comprehensive analysis across all ZT text functions. Across all test ZT functions, ECNJ3 outperforms both NSGA2 and NSGA3, as well as their chaotic only variance. Statistical validation using the Friedman test and Buffer-Roni-Dunn analysis confirms the superiority of ECNJ3, ranking it first overall with significant improvement. This suggests that integrating chaotic dynamic with estimated convergence province not only enhance convergence towards the Pareto from, but also delivers a diverse and stable set of solutions. Establishing yet CNJ3 as a robust approach for complex multi-objective problems. That's all. Thank you for listening.